Hello everybody. First of all, I'm really honored to be here and present our work in this dependency management dev room and FOSDEM. My name is César. I'm a PhD student at KTH Royal Institute of Technology in Sweden. And today I'm gonna talk about DepClean, an open source tool that we developed to detect and remove bloated dependencies in Maven projects. So let's start by giving a little bit of context about dependency managers in Java. Apache Ant was a successful build tool for Java, but it had some drawbacks, such as the lack of formal conventions regarding the project structure. It is also procedural in the sense that you need to provide information about what to do and when to do through the code in a given order, and therefore most of the Ant scripts are not reusable. Then Maven appeared as a build tool with a much more declarative build file called the pom.xml. Maven has a convention of where to place the source code, the compiled code, etc. Gradle is another dependency management tool for Java. It uses a domain-specific language based on the programming language Groovy, differentiating it from Maven and Ant, which use XML for its project configuration. Using the Maven dependency management tool has several benefits for developers. The main task of Maven is to build Java projects. This process is divided into several phases, which includes the compilation of the source code, the execution of the test suite, and the deployment of the compiled artifact to some external repository. The first step to build a Maven project is to resolve all the dependencies of the project. This process consists of downloading all the dependencies necessary to build the project and put them into a local repository. Once all the dependencies are downloaded to the local repository, Maven can execute the tests, add documentation, manage resources, and release the software artifact to Maven Central, which is the most popular repository managed for Maven artifacts. An important feature of Maven is that it guarantees the reproducibility of builds, since every build is based on the same pom.xml file. Since Maven provides a consistent structure of our project, so this allows us to implement additional tasks in the form of custom plugins. For example, to analyze the dependencies of our project. So let's focus on the dependencies. In this talk, we are going to provide an answer to the following fundamental question. How many dependencies do we actually use? Let's say that we have a project P. In the pom.xml, we declare 3 dependencies, A, B, and C. These are direct dependencies of the project P. But the dependency A has other dependencies, D and E, and dependency C has a dependency F. D, E, and F are called transitive dependencies of the project P. On the other hand, this project P declares the module Q in his parent, and Q declares a direct dependency G. So, in this context, G becomes an inheriting dependencies of project P. In summary, we can distinguish 3 different types of dependencies in the project P: direct dependencies, transitive dependencies, and inherited dependencies. This is the dependency tree of project P as interpreted by Maven. But let's see how these dependencies are actually used. If we forget about the dependency tree structure for a moment and look at the bytecode calls made by project P, we can see that there is a set of instructions in P that calls another set of instructions in the dependency A. And this set of instructions in A calls another subset of the transitive dependency D. Interestingly, we can also see that the dependency F is used by a subset of P. So in this context, the dependency tree of P is still the same, but there are dependencies that are not needed. P doesn't need B, it doesn't need C, E, or G. We call this bloated dependencies, and we strongly believe that they should be removed from the project. With this in mind, we developed DepClean. It is a tool that detects and reports bloated dependencies to developers. DepClean works in the context of a Maven artifact. It analyzes its whole dependency tree and produces a report with information about the usage status of each dependency in the project. These are two unique features of DepClean. There is a Maven plugin called the Maven Dependency Analyzer that provides a report about the status of usage of some dependencies, but it doesn't analyze transitive dependencies in the context of a given project, and it doesn't distinguish between transitive and inherited dependencies. Another important feature of DepClean is that it produces an alternative pom.xml file with all the bloated dependencies removed, so developers can use directly this POM file in their projects. And of course, DepClean is open source, so it is publicly available on GitHub. So coming back to our example, DepClean starts by looking at the part of P that calls third-party dependencies. In this example, there are two sets in F. One of them uses a subset of dependency A, and the other uses the dependency F. And as we can see, the project P doesn't use the direct dependencies B and C, so we can remove these dependencies from P. To do so, we just need to remove a couple of entries in the dependency declaration in the POM file of project P. Now we can see that the part of A that is used by P calls some instruction of the dependency D, but it doesn't call any API member of E. So in the context of the project P, which is the one that we are analyzing, the one that we are interested in, the transitive dependency D is used, while the transitive dependency E is blotted. Notice that maybe A uses E. However, in the context of the project P, E is not used because it doesn't exist any bytecode call to E in the part of A that is used by P. This way, E can be safely removed from A in the POM, which means that it will no longer be part of the dependency tree of P. On the other hand, DepClean reports that the parent module Q of P, as well as the inherited dependency G, are not necessary. In other words, there is no bytecode calls from P to any of them. So the developers of P can remove this parent declaration from the POM if they want to. I mean, it is safe to do it if the only purpose of having the parent module is to inherit dependencies. Although, as we know, there are many other reasons to have modules in Maven. But in terms of the dependency tree, this change will make it smaller. So at the end, P only uses 3 dependencies, A, D, and F. And the result of using DepClean is a smaller dependency tree with only 3 actually necessary dependencies. To sum up, the main objective of DepClean is for a given Maven project P to debloat its dependency tree in order to produce a smaller version of it without bloated dependencies. DepClean performs this task based on a static analysis of the bytecode calls. It doesn't need the source code of a project to run the analysis. It can analyze the bytecode of compiled Maven artifacts. DepClean is implemented as a Maven plugin. This means that it can be easily added to any continuous integration pipeline. It also provides several configurations, for example, to break the build if it detects any bloated dependency. This way, developers can protect the projects from the arrival of new bloated dependencies. Having DepClean in our toolset, one question arises immediately. How much dependency bloat exists out there in the wild, in the entire Maven ecosystem? Let's see a real example just to put this question in a proper context. This is the dependency tree of Spoon, a library for metaprogramming and source code analysis. It contains a total of 75 dependencies. As we can observe, there are both direct and transitive dependencies. Maven, as part of its standard analysis, excludes a total of 31 dependencies from its dependency tree. These are redundant dependencies, which basically means that they are duplicated versions of the same provider. After this step, DepClean performs its novel dependency analysis. It detects 13 bloated dependencies in the Spoon library. So basically, we can use DepClean to transform its dependency tree, we debloat it, remove all the unused dependencies, and obtain a much smaller version of it. And it is important to say that this process doesn't affect the build of a Spoon. It is still compiled, the tests are executed successfully, and all the rest of the Maven phases work as normal. Which is also very important, the removal of these bloated dependencies has a very positive impact on the size and the number of classes of this library. The jar with dependencies of the Spoon is reduced by 16.2 megabytes to 12.7 megabytes, which represent a significant reduction in the size on this of 27.6 and 24.7 of reduction in the number of classes. So far, we have seen the impact of using DepClean on the Spoon library, but what about the whole Maven ecosystem? Well, one thing that we know is that it is big. 2 years ago, we performed a study with the objective of constructing the most precise representation of the dependency relationships between all the artifacts in Maven Central. What you're seeing in this figure is part of the Maven dependency graph that we built. It contained 3.6 million artifacts in 2019. Based on this graph, we selected a total of 9,000 Maven artifacts as study subjects. This selection took into account several criteria, such as the diversity, which means that they belong to different Maven projects. Reused, the subset are used by at least one artifact through the direct dependency declaration, and they are also complex, which means that they contain class files which we will analyze at the bytecode, and they have at least one dependency with compiled scope. The selected 9,000 Maven artifacts contain a total of 723 dependency relationships, of which 6% are direct, 25% are inherited, and 69 are transitive. This bar chart summarizes the results obtained. Each bar represents the percentage of dependencies of each type, direct, inherited, and transitive, that are bloated in blue or used in orange. The key result from this figure is that 2.7% of direct dependencies are bloated. This is surprising because those are explicitly declared dependencies in the POM of Maven projects, which means that 2.7% of the dependencies that are declared in the POM are actually not necessary to build those projects. On the other hand, we found that 15.1% of the inherited dependencies are bloated. This means that there is a lot of dependency bloat caused by Maven inherited dependency mechanism. Perhaps a little bit less surprising, but still relevant, is that 57% of all the transitive dependencies are bloated. These are dependencies that are induced by direct dependencies as a result of the Maven dependency resolution mechanism, but they are not necessary, and therefore they are bloated dependencies. So, answering our motivational question, how much bloat exists out there? Well, we found that in our dataset of 9,000 Maven artifacts, 75% of all the dependency relationships are bloated. Also, 36% of artifacts have at least one bloated direct dependency declared in the POM. And 86.2 artifacts have at least one bloated transitive dependency induced by direct dependencies. This is a lot of bloat, but another question is, do developers care about it? To answer this question, we performed a user study. We selected 30 projects and used DepClean to analyze them and see if they have bloated dependencies. For the selection of this project, we follow several criteria, such as they must be open source, they should be active on GitHub, also popular, which means that they have at least 100 stars. We know that stars is a common criteria that means that projects are popular. They bear with Maven and contains dependencies. This workload shows the selected projects. Many of them are well known by the Java community, such as Jenkins, Flink, Neo4j, or Checkstyle. So we use DepClean to analyze this 30 project, and we made 30 pull requests proposing the removal of bloated dependencies. This pie chart shows the results obtained. As we can see, 21 pull requests were accepted by developers and merged into the projects. 5 pull requests were rejected, and 4 of them received no answer. In total, 140 dependencies were removed from the dependency tree of 21 projects. These results indicate that removing bloated dependencies is important for developers. They are ready to take action, and also that if we submit pull requests proposing the removal of bloated dependencies, they are likely to be accepted by developers. Let's quickly discuss an example of a project that we analyzed. DepClean found bloated dependencies in the core module of Jenkins. 1 bloated direct and 2 bloated transitive dependencies in this module. It also found direct dependency bloated in the CLI module of Jenkins. So we submit a pull request proposing the removal of all of these bloated dependencies. With respect to the bloated dependencies in Jenkins core, developers were reluctant to remove them. They say that past experiences removing unused dependencies have broken some clients. They agree that these dependencies are not used, but they don't want to remove them for compatibility reasons. What we can learn from this example is that bloated dependencies should be removed as soon as they appear, because otherwise some clients may depend on them and it will be more difficult to take action without breaking those clients. With respect to the bloated dependency that we found in Jenkins CLI, this is the exact code change that we propose in the POM of this module. It is basically the removal of common codec. And this change was accepted and merged by developers of Jenkins CLI after a while. To summarize, there is a lot of code bloat out there, caused by the transitive dependencies that are induced as a result of the Maven dependency resolution mechanism, caused by the multi-module architecture of Maven, and also caused by software development practices. Developers care about this issue for multiple reasons. For example, for security, having fewer dependencies decreases the attack surface of the applications. Also, for performance, having smaller artifacts make it easy to deploy and share them over the network. And DepClean is a useful tool to automatically detect and remove bloated dependencies from Maven projects. So now, let's see a quick demo of DepClean in action. Okay, let's analyze this Maven HBC project of Twitter with DepClean. It is a Java HTTP client for consuming the Twitter's standard streaming API. As we can see, it builds successfully according to the Travis continuous integration service. So let's clone it using our terminal. Now that the HBC project has been cloned, let's execute the Maven build locally. As we can see, all the modules build successfully. Now, let's focus on the HBC core module. The Maven dependency tree command allows us to visualize the dependency tree of this module. It contains several dependencies. I have already installed the DepClean Maven plugin in this computer. So let's execute this plugin with the create POM debloated flag set as true. This is going to produce a debloated version of the POM of this project. DepClean has finished its execution. We can read in the provider report that the transitive dependency commons codec is a potentially unused dependency. Accordingly, DepClean creates an improved version of the POM without this dependency. And when doing so, it follows the best practices regarding dependency declaration. Let's have a look at the POM debloated file that has been created. As we can see, the transitive dependency commons codec has been excluded from the direct dependency HTTP client. Now we have two versions of the POM, the original and the one debloated by DepClean. Let's rename the debloated POM and replace the original POM with it. We should build the project again and check that the changes introduced by DepClean doesn't affect the build. As we can see, the build is successful. Let's have a look again at the dependency tree. As we can see, the unnecessary dependency commons codec is not part of the project anymore. So we have successfully removed the debloated dependency from this project. Thank you very much for watching.